In problem 15.69, we have a can that has height h and it's full of water. And then a hole is drilled in the bottom of the can, and the water is allowed to flow out, and I'll denote that as velocity 1. Now I'm going to show the cross-sectional area of the can as A naught. This represents not the diameter, but the total cross-sectional area. And the same thing for the hole at the bottom of the can. It'll have a cross-sectional area of A1. This is A naught right here. As the water drains, the level of the water will begin to fall, and that the level of the water is denoted as Y. And in a differential time dt, the water level will drop a value of dy, and the volume that comes out that leaves the can is the volume of water that must flow out in this time interval dt. The area of this hole is much smaller than the area of the can, and this causes this velocity of the surface of the water to move down very slowly. It's so that velocity, the velocity that the water level drops, is very small. So we're given the areas and the fact that A1 is very much smaller than A naught, and the height of the can. And in terms of these parameters, we'd like to know how much time it takes for this water to drain out of this can. One of the things to consider is the fact that the velocity of fall of the water is very, very small. Okay, so we're going to treat that velocity as essentially zero. So if we look at Bernoulli's equation and compare the parameters at the surface of the water and then at water coming out of the hole, the pressure at the top and the bottom due to the atmosphere are the same. So the pressure at the wherever the level of the water is, the pressure here, okay, due to the atmosphere, plus here's a potential energy term, the density of the water in the can times the acceleration due to gravity times the height, okay, plus, all right, we're going to ignore the kinetic energy terms because the velocity is so small right there. That's got to equal the pressure at the bottom of the can plus the kinetic energy term due to the water flowing out of the can. And then there's no potential energy term because y equals 0 at the bottom of the can. Okay, so here's what Bernoulli's equation looks like. And since the two pressures are the same, we're left with this expression right here, but we can factor out the density so that the velocity of the water at the hole is just simply equal to the square root of 2 times g times the height of the water. I'm going to use this symbol here to denote the volume of the water that's left in the can at any instant. And that will be equal to the cross-sectional area of the can times the height of the water that's still in the can. This volume will change as water flows out, and the differential change in that volume will be equal to the velocity of water that flows out of the can, and that's the velocity at the bottom of the can times the cross-sectional area times the differential length of time. This basically represents the volume, okay, the height times the cross-sectional area in the time interval dt. Now that change in volume also occurs because water's flowing out up here. You know, the height is getting lower, okay? So if the height changes by an element dy, if I multiply that by the cross-sectional area, that's also equal to the differential volume. So So I could take this equation right here now and simplify it and get the rate of change of the height in terms of the elapsed time. So if now what I need to be able to do here to find the total elapsed time is do an integral, okay, over the time interval. Then I've got to do an integral over the differential in height. And so I have to get everything in terms of y on the left-hand side of the equation, constants, and then t on the right-hand side of the equation. So when you solve this, you get this equation here for that shows the relationship between y and t. Now, if you want to solve for the elapsed time, you're going to have to perform the integral of both sides of this relationship here. So I'm going to show you that, and I'm just going to show you the integral and let you work on this. And if you do the integral on the right-hand side, that's just simply the constants times the elapsed time t. You have to evaluate that from 0 to t. But then on the left-hand side of the equation, you've got to integrate over the y variable. And remember that the water starts out at h and decreases all the way to 0. So if you integrate this side of the equation, you should be able to solve this equation for t and get the desired expression. And I'll let you finish that problem.